We work in the problem setting of rehearsal-free continual learning. Typical solutions for continual learning require rehearsal of previously seen data, which increases memory costs and may violate data privacy. Recently, the emergence of large-scale, pre-trained vision transformer models have enabled prompting approaches as an alternative to data rehearsal. In our paper, we instead propose to learn a set of prompting components which are assembled with input condition weights to produce input condition prompts, resulting in a novel attention-based end-to-end key query scheme. We show that our method outperforms state-of-the-art prompt-based approaches by as much as 4.4% accuracy on continual learning benchmarks. Keep listening to learn more. So we work in the problem setting of rehearsal-free continual image classification. Prior work learns prompt tensors, which are inserted into an ImageNet pre-trained backbone and directly optimized with a classifier head for continual learning. Because the backbone is pre-trained on ImageNet, we evaluate on a dataset such as ImageNet R, which is far in the distribution space from the original ImageNet pre-training dataset. And the problem with prior approaches, such as learning to prompt L2P or DualPrompt, is that they use a clustering-like operation for prompt selection instead of some type of end-to-end optimization. So how does this work exactly? Take the classic multi-head self-attention. Just like prior works, we use prefix tuning instead of prompt tuning for our work. Specifically, we are going to pre-append the projected key and query values from the multi-self head attention with learnable tensors. How are these selected? How are these inserted into the model? So, prior work, such as DualPrompt and L2P, have a key query selection mechanism. Specifically, for every input data, a key is matched to an input query. This key is associated with a value, where these values are the actual prompts that are inserted into the pre-trained model. Importantly, with L2P and DualPrompt, the key and values of the prompts are learned in separate optimizations. Specifically, the prompts are learned with gradient flow from the model with classification loss, whereas the key mechanisms associated with the prompts are learned with a separate clustering-like optimization. This motivates our work. We instead replace our query with an attended query, which is then associated with a weight. Given these weights, we actually weight individual prompting components rather than having a hard key query prompting selection mechanism. Every prompt inserted into our model is a weighted summation of our learnable prompting components. The TLDR is that rather than expand these prompts in a pool mechanism like prior work, we expand them in a new optimizable component dimension with attention-aided component weighting. Here is another high-level way to look at our work. Where the past work has a query function that comes in and selects a prompt from a pool, we replace this with our weighted attention-based mechanism prompt components. Specifically, given some input image, like this handsome dog on the top left, we process it with a query function. This query function is actually just the frozen pre-trained transformer backbone without any prompts inserted. We then multiply this with learnable attention vectors. This gives us an attended query, which has a much easier properties to cluster with and work on. We multiply this attended query with learnable prompting keys using cosine similarity. This produces our component weighting. Now, each of these component weightings are multiplied with our prompt components, resulting in a final prompt which can be inserted into the layers of our models. When each new task comes, we expand our prompting components and associated learnable tensors. We freeze everything from past tasks and we only learn and update the classifier and the expanded components. What kind of results did we get? On the ImageNet R benchmark, we can see an upper bound accuracy of around 77%. The prior state-of-the-art we found to be 71.49%. Our method, CODA-Prompt, we found to strongly outperform the state-of-the-art on this benchmark. We showed two variants, CODA-Prompt Small, which has the same number of learnable parameters as DualPrompt and LTP, and then our regular CODA-Prompt, which has parameters that were directly chosen with a hyperparameter search. The takeaway here is that our method CODA-Prompt is state-of-the-art for the replay-free image classification. But why? So why does CODA-Prompt work? We found that if we increase the prompt length to increase the number of learnable parameters, we have saturated performance with all prior methods, learning to prompt, DualPrompt, and our method as well, CODA-Prompt. Increasing the prompt length does not help. Instead, we found that increasing the number of prompt components, which is our contributed new dimension in which we can expand on, actually increases the accuracy of our method. So this means that our new dimension is behind our performance and accuracy increases. We invite you to come check out our poster or read our full paper, where we have many more experiments and results, including 3 different benchmarks, varying task lengths, and ablation studies. Thank you for listening to this talk. We look forward to seeing you at the conference. You can check out our main text by following this QR code link. This will also bring you to the code page as well. Thank you again for watching.